against each other, see which one will yield the highest score for each design alternative. And from this we can see that the pulley system is the best. So since we're going with this, we thought we'd look into other ways on calculating the speed. So we're going to use a speed sensor which has already been come up with. We do not want to reinvent the wheel.
Don't say that it's already been come up with.
What?
Oh, sorry. Forget it.
For the electron, but hasn't someone already made that? Yeah. Which is why we, yeah, okay. And so this is where it turns into the sixth design alternative. Here's a picture of the prototype. Pretty much we have some fixed pulleys up in the top right, and we have the motor in the back connected to the friction pulleys here. And so here's a picture of how the friction pulley and the pulley system works. Down here in the bottom right, we have a picture of our motor connected to pulley number 1. So right here we see we have a 1-to-1 advantage. The 1 gets transferred over here. And from this 2 and this 1, we now have a mechanical advantage of 3 right here. So this 3 comes around here and here, which now makes 6, which is right here. And the 3 that continues through this. And so now you have 3 plus 6, and now you have a mechanical advantage of 9. Now we have some stress analysis. From our stress analysis, we found that the yield strength is about 29,000 PSI, and when we ran it in FEA and did actual analysis on it, we came up to 10.2 thousand. So our stress levels are well within our limits. Here's a picture of our prototype. You can see that we have our electronic system and our pulley system in place. And here's a more open view so you can kind of see the nightmare that we have in terms of circuitry. And oops, I'm going the wrong way. Alright, so here is a video. Chris is going to actually actuate the brake by speeding it up. And so you can see in this video how the pulley system works. So he's going to be speeding up and speeding up and speeding up. Once it gets to the exact speed, you see that this is going to pull on the brake. When he lets it off, you see it travel back and reset back to home position. So right now it's resetting back to home. And then, so once it resets back to home, it's no longer engaged and you're free to bike freely.
But not going over the speed limit.
Exactly. Exactly. So our prototype is composed of 3 main components. Our box, which has our rigid pulleys, the motor, and the electronics fit in place. We have the pulley system, which incorporates the mechanical advantage, and the new speed sensor design is the last one. The prototype box, we did most of our machining in the machine lab, except it's with plastic for most of the pieces. We ran into a couple difficulties machining plastic and thin materials, is that it's really hard to work with and things like to break. Our prototype electronics is composed of our Arduino computer system, which is basically the brains of the operation. It keeps track of everything. The stepper motor is what actually gives us the muscle. It pulls on the string, which pulls on the brake. Our reed switch is pretty much our speedometer, and it just tracks our speed. And the potentiometer is this last one down here, and that is what allows us to change the designated speed and the and tire radius.
And what?
Tire radius. So if you have a different size tire, you can use it. Here's a picture of the Arduino. This is the brains behind it all. Here's a picture of our stepper motor, which is the muscle. And then we have a reed switch. This is basically our speedometer, and how it works is we have 5 volts set to this side, and this reed blade is connected to our Arduino. And every time, and this is going to be mounted on the tire, and then there's going to be the receiver, no, the transmitter is on the tire, and this is on the frame.
No, that's done. That whole thing is done.
Okay. So what runs by it every time we spin?
A magnet?
Okay, so we have a magnet that runs by
don't say
it.
transmitter, don't say receiver. Those things are gone. They're
Okay.
going to confuse people if you say that.
Okay, so this is just the reed switch. This is mounted to the frame. Yeah, frame, magnet to the spokes. Right. Okay. And every time the magnet runs by, there's an overlap, or there's a gap in between these two. Every time the magnet goes by, it closes the system, and it can track your speed based on every time it goes by. Here's a picture of the potentiometer, and we have a video for that.
The user input controls to set the tire radius and the maximum miles per hour are these two potentiometers right here. And you can see the readings showing up on the screen right here. So what I'm going to do is if I turn one of these knobs all the way to the right, it sets the minimum value, and which is 5 miles per hour for the speed. If I start turning it, every blink indicates another miles per hour above 5 miles per hour. So if I blink it twice, it's set at 7, and you can see the values adjusting here on the screen as I turn the potentiometer. And I'll do the same thing for the tire radius. Turn all the way clockwise is 8 inches. Every blink above that is another inch, so that would be 9 inches, 10 inches, 11 inches, and you can see it showing up here.
Okay, so that's basically how that's going to work. In our speed control system, it pretty much, the computer calculates the speed, and the stepper motor will gauge at whatever designated speed we have it set to. Then the computer will check that speed again, and then it will act accordingly. So if it's above this speed, it will actuate the brake more, and if it's at less, it will deactivate the brake and let you ride freely. And then we're on to prototype testing, where I'll hand it off to Chris.
All right, thank you, Kenton. Hi, everybody. My name is Chris Kirby. I'm going to be talking about the actual testing that we did of our system. So basically, what our testing plan was is basically these things you see listed. The things we did is we wanted to test the individual components to make sure that they worked before we integrated the entire system. So part of that was testing the pull force of the motor. Was it strong enough to do what we needed it to do? Test the mechanical advantage of the pulley system. If we pull on with 2 pounds, did we really get 18 on the other side of it? Speedometer test. Is the speedometer accurate? We want to test the braking ability, so we put various weight riders on it. We tried one kid who weighed 85 pounds. I myself rode it. I'm at 140. Nick tried it. He's at 154. And then we also need to make sure that it engages at the correct speed. So for as far as testing the mechanical advantage of the pulley system, we actually measured it. We hooked it up to spring scales. We pulled on one end and we measured the force on the other side. We got 8 to 1. Theoretical was 9 to 1. That's very likely due to the friction that we have in the pulley systems. We had to have a track on the actual pulley. So these washers you see are actually not the pulleys. There's a pulley inside of there, and these washers are just to keep the thread on the pulley so it doesn't fall off. That's where extra friction comes from. Our speedometer test, what we did is we had a separate GPS system that measured miles per hour, and we hooked it up to our bicycle, and we rode it. And we knew that the Arduino thought it was at 10 miles an hour as soon as we heard the stepper motor engage. So when we hear the stepper motor engage, we read the value off of the GPS, compare the two values. We did that, we got about 3.2% average error. It's pretty accurate. This is just a chart of the tests we ran. These are the trials, 1, 2, 3, 4, 5, all the way up to 10. This axis is miles per hour, so first trial, that's our reading. We took the average, the orange line is our theoretical. So we wanted to be at 10, these are our values. This chart shows our percent error, it's about 3.2%. So like I said, fairly accurate. And here's a test, worst case scenario. The worst case scenario we can imagine is a kid going downhill, pedaling as hard as he can while the brake's still engaging. And here's what is happening. And you should do this.
Yeah. I didn't want to dive in front of you here, but I can do it easy there. It's all right.
And you'll see he's working really hard.
Dude, he was working it.
And he did not get going that fast.
Gee, Mom, you ruined all my fun.
Yeah. Now what we did do is we did have him look at the speedometer and record the maximum speed he got up to. The brake does take a little bit to engage. It takes a couple seconds actually. The fastest he could go, we set the speed cutoff at 7 miles an hour. He was able to, for a small moment in time, actually get all the way up to about 14. So he would kind of fly past the system, get up to 14, it would start bringing him back down. So basically that's kind of what we're looking at. So it's not instantaneous. We didn't want to just clamp the tire down right away and send him flipping over the handlebars. So there's a little bit of cushion there for him to work with. We ran 2 tests, 7 miles an hour, 10 miles an hour, same rider. His maximum speed was about the same in both cases. He's about 14.5, somewhere around there. So this is a video